Hello. Today we'll continue our topic least squares problems. Last time we studied how to solve least square problems using linear algebra approach. So today we will consider another approach, how to use calculus to solve such problems. Okay. But before that, I want to remind you uh, the previous approach. So I see that many of you did not send me homework solution. So it's worth to repeat that. But I will not solve that problem for you. Maybe next week, sometime I will solve that. So the previous approach was as follows. You have to solve, you know, this system, right? But suppose that this system does not have solution. uh, our 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 problem is to find some extra, such that the norm of ax minus b is minimum, right? Is minimum. So the first step we did last time is we need to find a transpose, right? And then we applied a transpose to both sides of the equation 1. So the equation 1 becomes a transpose a x equal to a transpose b. But last time we separate these two steps. First we find the product ATA, and then we find ATB, right? From here you can see that actually this metric is square. This metric is square, and and so once we have that, we can think like we can use several methods to solve such systems, right? But basically, you if it's possible, you can find ATA to -1, right? And then you apply ATA to -1 to both sides of the second equation. ATA x equal to a ta to -1 ATB, right? And this is just identity. This is just identity. in x equal to ATA to -1 ATB. So that is your solution. X star equal to ATA to -1 ATB. So basically, you have to do a lot of, matrix multiplication. So if you have this formula, just go ahead to apply that. And if you know how to use calculator, or you go to internet, they will do some kind of matrix multiplication online, right? And then with the matrix A, you can find the solution right away. Okay, but that's what we don't want. We need to know how to solve all such problems. Now let's look at this problem from another point of view. So basically I need to minimize my functioning here, right? The norm of ix minus b, and the norm of this can be calculated in Rn, right? In Rn, and we know how to do that. Let me remind you, right? If you have some vector u, which is u1, u2, and then un, the norm of u is just square root of u1 square plus u2 square plus so on, plus un square. So basically, if we write matrix A's in the column form, right? So we have the following one: ax minus b. That is what? That is x1, a1. Oh, let me write a capital letter, right? A capital letter plus x2, a2, plus so on, plus xnan, the norm in here, minus b, where a1, a2, and so on an are columns of A. So I hope you still remember that. Let's say this, right? If we write, let me explain this notation. If we write A as A11, A12, and so on, A1n, right? A21, A22, and so on, A2n, and AM1, AM2, AMN. And this is X1, X2, and so on, Xn, okay, equal to B1, B2, and so on, Bn. We denote this by the column A1, the column A2, the column AN. So basically, you know, when you rewrite the system AX equal to B, that will look like X1 A1, right, plus X2 A2, plus so on, plus Xn AN equal to B. And we know, you know, it says B is a linear combination of columns A1, A2, AN, right? So we know about that, you know, in very first chapter when we study matrices. I can write here B is a linear combination of columns of A. So basically, you know, solving this system means we just try to find x1, x2, so on, xn, such that B can be represented as linear combination of columns of A. But as we suppose that this system will not have solution, right? So that's why we can minimize this value. We can minimize this to find, you know, the most fit, right? So I can write, yeah, another form of the least square problem is, you know, phi x star equal to x1 star, x2 star, and so on, xn star, such that x1 star A1 plus x2 star A2 plus so on plus xn star AN, oh, here minus B, is minimum. So that is another form of least square problems. All right. So, you know, now we have all vectors. We can find the norm of the vector, and then you have some function. And your function will be function of n variables. Okay. And then, you know, if we use some knowledge from calculus, we can solve that problem easily. That's what we plan to do right now. Okay. But I will demonstrate that via an example so that, you know, it's easier for you to follow. All right, let's consider the following example. Let's solve least square problems for the following system: Ax equal to B, where A is equal to 2, negative 1, 0, 0, 1, and 2, and the B is 1, 0, negative 1. Okay, so basically, if we write in the column forms, the problem looks like x1, 2, negative 1, 0, plus x2, 0, 1, 2, minus 1, 0, negative 1, and we need to minimize this function. So in order to minimize this function, we just minimize the square of this function, because, you know, and we know that, you know, when we calculate the norm of this vector, we will have square root, right? So this problem is equivalent to the following problem. Just minimize. I will copy everything here, everything here, everything here, and then square, right? Okay, so let's find this vector and then find the square of the norm, and we'll see what we get. So I can write the norm of the following: 2x1, x2 with 0 is just 0, minus 1, right? That is the first coordinate. The second one, negative x1, and then plus x2 minus 0, which is 0. That's good. x1 with 0 is 0, 2x2, and then plus 1. I would write like this, so just, look more beautiful, okay? And we need to minimize this function. And we know the norm of this is just equal to 2x1 minus 1 square plus x1 minus x2 square plus 2x2 minus 1 square plus 1 square, right? And our problem is to find the minimum. So let's denote this function by fx1, fx2. Now let's find critical points of this function. Okay, let's find critical points of this function. In order to find critical points, we need to find partial derivatives. We need to find partial derivative. Okay, so what is that? This function has two variables, x1, x2. So when we differentiate this function with respect to the x, and we look at x2 as a number, so we will have partial derivative of this function with respect to x1. Make sense? Okay, let me show you one term, right? Let me differentiate one term with respect to x1, and then you see. I want to find partial derivative of this function with respect to x1. Okay, so I will differentiate the first term right here. The first term has only x1, no x2, so it's easy. I just differentiate with respect to the x1. So I get 2 times in here, and then 2x1 minus 1 times 2. I use the chain rule in this situation. We have 2. That is the power. We bring the power down, right? We bring the power down. And then I keep the inside function, and then I differentiate the inside with respect to x1, I will get 2. So that is the derivative of the first term. All right, so how do we do the second term? Oh, okay, here I have to mention, I rewrite x1 minus x2, right? But in here we have negative x1 plus x2. That is the same if we have squaring here. So that's okay. Now I differentiate the second term with respect to x1, and x2 is a number, don't forget about it. I get the following: plus 2 times, I keep the inside x, which is x1 minus x2, and I differentiate the inside with respect to x1, I get 1. You see? And then the last term does not have x1, so the derivative of the last term with respect to x1 is just 0. Okay, I hope you still remember this. We did this one time. But anyway, yeah, let's do that together, and let's simplify this. I get 2 with 2 will be 4. Here have 8x1 minus 4, right? And in here I get 2x1 minus 2x2. So that is 10 x1 minus 2x2 minus 4. Now let's differentiate the function with respect to x2. So in order to find partial derivative of this function with respect to x2, I have the first term does not have x2, so derivative is 0. The second term, so I do the chain rule, 2 times x1 minus x2 in here times negative 1, because the derivative of negative x2 is negative 1. Okay, so for the last term I have 2 times in here, then 2x2 plus 1 times 2. Let's simplify this. I will get negative 2x1 plus 2x2, and then here I have 8x2 plus 4, right? And that is negative 2x1 plus 10x2 plus 4, right? So now we already have partial derivatives of this function with respect to x1 and x2. The next step is set them equal to 0. Okay, now I set them equal to 0. We set derivative equal to 0. Set partial derivative equal to 0. This step is, similar to the case when you put y prime equal to 0 to find critical points. Make sense? Because we need critical points. All right, so we will set this part and this equal to 0. We will have a system of linear equations. So I get 10x1 minus 2x2 minus 4 equal to 0, and negative 2x1 plus 10x2 plus 4 equal to 0. I can simplify, 2 from 2 equations, and I will write in the following form. I will interchange 2 equations. So from the second one in here, I get x1 minus 5x2 equal to 2. And from the first equation, I will get 5x1 minus x2 equal to 2. Or if you write in the matrix form, that would be 1, negative 5, 5, negative 1, and here 2, 2. We know how to solve such system, right? I hope so. So we multiply the first row. With negative 5 and add to the second row, right? I have the following. This is just 1, negative 5. Here is 2. This is 0. And negative 5 with negative 5 is negative 25. Up 25. And then minus 1 is 24. And 2 with negative 5 is negative 10, right? Plus 2 is negative 8. And then we divide both sides of the second row by 24. We get 1 in here, and we get negative 8 over 24, right? Which is negative 1/3. Okay, which is negative 1/3. And here I get 1, negative 5, and 2. And now I multiply the second row by 5 and add to the first. By 5 and add to the first to make negative 5 0. So I will have this just equal to, okay, let's write here row 2, negative 5, and add just 5, add to the first. I get 1 0 0 1, and then here I get negative 1/3. Here should be 2 plus negative 1/3 times 5, right? Okay, so you can do this computation. You get 2 minus 5 over 3, you get 1/3. So we already have solution, right? We have x1 equal to 1/3 and x2 equal to negative 1/3. And this is critical point for the function f, x1 and x2. We did a long way, but actually, the only thing we need to do is find correctly partial derivative. You see that? And once we found x1 is 1/3 and x2 is negative 1/3, we can plug x1 and x2 into this function to find the minimum value of this. Okay, and what is x1 and x2? Actually, x1 and x2 is x star. This is 1/3 and negative 1/3. That's how we can use calculus to solve this problem. Okay, so you know this is the second approach, and I hope that it is clear enough. It is clear enough. The good thing, in such approach, when you calculate the norm of this vector, you have polynomials. I mean this norm. You have polynomials like this. Make sense? And let's mention one more thing. Our matrix has two columns. You see this? Our matrix has two columns. So that's why, at the end we will have two variables. At the end we will have two variables, x1 and x2. All right. So I think I can stop my lecture, today lecturing here. And before that, I would like to mention one more thing. Actually, this approach, in some sense, is equivalent to this approach. It's interesting, right? In some sense, is equivalent to approach from calculus. The only thing is, we just use calculus tools, and in the first approach, we use matrix multiplication. All right. So on the lecture on Friday, probably we will solve a couple more problems, and we will summarize two approach. Okay, before we move to the next topic. All right. Thank you. And please, if you have any question, send me an email, and do homework, please. All right.